there are no radioactive waste products because you're just dealing with varied forms of hydrogen.
So if this is cold fusion, there's no more worry about nuclear waste from nuclear power plants, there's no more worry about climate change and the greenhouse effect. We're sorted.
Yes, I mean, this would be the breakthrough that the world has been waiting for. This would be the source that actually powers all of the stars, able to be run on our very own power stations in our very own homes. We wouldn't have to worry about waste products. We wouldn't have to worry about anything for this generation or the generation to come.
It's amazing stuff. I'll be crossing my fingers. I guess you probably will be too. Thanks so much, Vic.
Nuclear physicist consultant for DOE was a little nervous. He would every now and then he'd be talking about, hey, yeah, listen, and then he'd all of a sudden, wait a minute, I need to hedge my bets a little bit here. He never did talk to us, by the way, in advance of doing that. He did get some of our papers and read our papers, but he never did talk to us before he did that, or we could have answered some of the questions that he was trying to waffle on. Showing you what has happened, in 1989, fusion or illusion was the cover on Time magazine. Current Science is published in India. It's the India equivalent of Nature. Our high energy neutrons were on the cover in the January 2007 edition, and low energy nuclear reactions source book 2009. Our DT fusion neutrons are on the cover of that book. Next. I mentioned, 25 or so peer-reviewed journals and a lot of conference proceedings and things like that. We don't even count those. Some of the places where we've published, Journal of Electrodynamic Chemistry, Nature Wissenschaften, Einstein published there, several Nobel Prize winners published there, European Physics Journal of Applied Physics, several Nobel Prize winners have published there, Thermochemical Acta, Generative Fusion Technology, and so on, and then a couple of books. So we have been successful in getting our papers published. Next. Some of the replications, I mentioned Mel Miles and heat and radiation. Tritium was Dr. Bockrist at Texas A&M. High energy particles, these were all people that were involved in the Galileo project that was conducted a couple years ago. Next. Evidence of heat generation, the calorimetry, IR images indicate that heat's being generated, and the fact that it's occurring in many explosions rather than just a gradual heat up of the electrode, which is what you would expect if it was being generated, if that was caused by resistance in the electrode. Low energy radiation emissions, X-rays and gamma rays and so on as we've done the experiments. Next. Tritium production, I've talked about that, and transmutation in E and B fields. Next. The high energy particle work, the CR39, a lot of work that we've done there, and a lot of replications and so on, and all consistently indicating that we are producing high energy particles, including tritons, protons, neutrons, helium-3, and alphas, things that are consistent with reactions that you would expect. Next. So these experimental results suggest that as the that we do have the potential for unlimited energy here. And by the way, when he said all the ocean's water, realize that we're 1 million times more efficient than oil. So for every 1 million gallons of oil, we'd only need 1 gallon of ocean water, so it can last for a long time.
But the oil is already in the ocean.
Yeah. Right. So anyhow, provides low-cost energy to deliver fresh water. Several applications. Next, and quoting from the DOE consultant on the brink, he said, this could be the breakthrough that the world has been waiting for. And certainly, if we're successful, we believe that's the case. Current status. Clearly, we're producing events that are nuclear. So, one of the first questions was, is it nuclear? Because if it's chemical, well, there's not that much interest. We already know how to burn things. We know a lot about chemical reactions. This really doesn't get interesting unless it is nuclear. And we have a lot of evidence that's nuclear, including more heat than you can generate through chemical means, transmutations, and particle emissions, and so on. The nuclear ash that, in fact, can only come from nuclear. Next. The next step is we need to scale the experiments and increase the flux so that we can get the applications. Right now, we're not producing enough high-energy neutrons that we would need for some of the applications that we would like to use. Next. Here's some concept applications. One, we call it a green nuclear energy reactor, GNE. You say GNE fast enough, it's Genie, and Genie in a bottle for our cold fusion. The Genie reactor, the concept here is we're going to build a fusion, fast fission reactor, only we're going to generate the fusion from our cold fusion cell to generate the neutrons that we would then use to fission the target material. And there's like what that means is we don't rely on a chain reaction for the events, and there are some definite advantages that, in fact, we can consume. We don't need enriched uranium. We can fission native uranium, natural uranium. Genie technology consumes the hazardous waste and significantly lower cost because you don't have all of the safety factors associated with preventing a potential meltdown or a runaway. Next. And Genie technology addresses both energy and environmental issues at the same time because we're not producing nuclear waste, high energy nuclear particles. Next. This Wednesday, I just added this view graph. The San Diego Union Tribune this week had an article on Renaissance for nuclear power. And it talked about how power plants around the U.S. are springing up, and nuclear power plants. San Onofre, just a few miles from here, is one of the 104 currently operating nuclear power plants. However, California is not joining in on that rush because there's a 1976 law that prohibits any nuclear power plants in California until the federal government has come up with a way to deal with the long-term hazardous waste storage. And here's a quote from one of the people I talked to. He said, at this point, legislatively, there does not appear to be any interest in nuclear energy. This is in California. Next. But, of course, our technology does not produce long-term hazardous radioactive waste. Next view, right? And I mentioned the way this happens. We use our reactor to generate the high-energy neutrons. They bombard the target nucleus, which can be, like I said, unenriched uranium, native uranium. That fissions. If this is a long-term hazardous waste problem, we can continue to fission that until we end up basically with materials that don't have long-term radioactive waste issues. So it combines, they say fusion is energy poor, neutron rich. Fission is energy rich and neutron poor. We are taking advantage. We're generating the neutrons from our process and getting the heat from the fission process. Next. Radioactive hazardous waste. Here's this picture that you just saw previously, only this time the target nucleus would be that primarily U-238 and an actinide associated with the hazardous waste. In 2007, the U.S. had 50,000 metric tons of spent nuclear fuel. In fact, a typical fuel rod only consumes about 4% of the energy before it's taken out. In order to maintain the chain reaction, you have to enrich the U-235 percentage in the fuel rod. That takes energy. Then once you get the fuel rods together, you have to, if you get them too close together, that's called a meltdown. If you get them too far apart, it's called a fizzle, or the reaction fails or stops. If you really get them too close together, it's called a bomb. This radioactive waste is sitting out there. In fact, now there are laws against even shipping it. As you know, Yucca Mountain has been shut down. The plans to store it there. So as a result, typical conventional fission nuclear reactors are storing this material on site. That means if you've got a reactor that's been operating for 10 years, and I think most of them have been operating at least that long, I'm not sure when the last reactor was built in the U.S., they have stored on site spent fuel rods from 10 years of activity where they've only consumed 4% of the energy. What that means is that there's 96% of the energy still in there that we can take out by doing this. So if you've got a reactor